Hi guys, today we're going to start on inorganic chemistry for your A2, and here is the first topic here. Right, let me just put down the okay. Here, right, for transition elements. Okay, we're going to study the physical and the chemical properties of transition elements. Right, and here it says first of all, talk about the physical properties. And it's only for the first set of your TM, titanium to copper. Okay, now you look at this here, right? From titanium, all right? Titanium to copper. Remember, this is the S block, right? Why? Because the last shell to be filled is the S. For example, this is 1s2, 2s1, see now, okay? Beryllium is 1s2, 2s2, see now, it's the S block. Here, of course, from here to here is called the P block. This is P block. Because why? And here, boron, okay, is 1s2, 2s2, 2p1, see now, the P orbitals are being filled. From here, scandium right onto zinc. It's called the D block. After we'll see it, okay, I'm going to show you the electron configuration for this whole thing here. But why is scandium and zinc, even though it's a D block, it's not included in the as a transition metal? Okay, you see this afterwards. Okay, so here you can see the first set, which is from titanium to copper, right? Now it says here, but first explain what is meant by transition elements in terms of D block. They're very specific, no, okay? Because in the marking scheme, they always include this one. Transition elements must be number one, an element. Remember, it's an element, right? It's not. They don't define it as an ion. It's an element. That means, for example, titanium Ti. Not Ti2 plus or Ti3 plus. It must be, not this one here, must be the element, right? In terms of D block elements. And they must form one or more stable ions. Number two is they must form one or more stable ions. Now here we talk about the ions 2 plus or Ti3 plus. And the ions must have incomplete d orbitals, right? So the 3 points for this definition. Okay, now let's go to here first. Now here, well, we can maybe talk about this first. Okay, here we forget the sketch of d orbitals first, because later we can talk about that in the color. State electron configuration. Okay, for each of the first row of the elements and the ions. Okay. So let's talk about this first. Right now, here I've got definition. Okay, right now, this from the book, so it is very detailed. Okay, it's one of the first thing, of course, is a D block element. D block element. Okay, right. As I say, these are the D block. These are the elements that form some compounds. Now, a compound is formed. Remember, these are metals. Okay. Metals, of course, no charge, right? They are neutral. When they form compounds, they normally combine with what? With non-metals, plus non-metals. And of course, this will lose electrons, right? Lose electrons, and they become positively charged. Okay, so in this case here, right, compounds means positively charged ions. Okay, in definition, they use ions. Okay, which means they are also positively charged ions. Which one or more, some here means one or more. One or more. Okay, the compounds in which there is an incompletely filled subshell of the electrons. Right, now let's look at the question on this definition, 5. Okay, explain what is meant in terms of transition element. Okay, 1 mark. I'll give you 2 definitions here. Right, it says here, an element forming one or more, you know, an element, they say an element here, right? An element forming one or more ions, you know, ions, one or more. It must have at least one, okay? With a partially filled or incomplete filled D shell on one mark. So 2 points here, right? They want hit 1 point and 1 point here, okay? But they didn't say a D block element, but you know, better to say a D block element. Okay, so another one is here. You can see another definition is here. An element, here they use an element. Okay, I should have done this earlier. Okay, an element, but of course you can say a D block element. D block element forming one or more stable ions, you know, ions compound, or you say it's with partially filled D or incompletely filled D orbitals. Okay, so 2 important points you must say: it must have a stable ion, right? And the ions must be partially or incompletely filled D orbitals. All right, so this is for definition. Okay, now let's go back to there. Now, okay. Right now, before we see why scandium and zinc are not included inside, we have to look at the all this electron configuration, right, of these substances here. I've got another one here, which gives better. Now, remember this is scandium, right? Scandium here, scandium, and you see scandium here is 21. Okay, now argon here is 18, so argon 18. The next shell to be filled is, of course, now this 3s is 4. Go to 4s. 4s2. This is 18, 20, and then 3d1. See now, okay? So together, this 3 here. So 3 plus 18 equals to 21. That's why it's 21. So this is your scandium. Of course, titanium will be 3d2, right? So you can see here, I did all here so to make it time easier for us. Stay there. Yeah. Right? So scandium is Ar. Okay. Now, normally, you know, this is put in this order, but you can also use like Ar. Okay. 4s2 and 3d1. See, normally when you fill the 4s first. 4s is further away from the nucleus, but lower in energy than 3d. 3d is nearer to the nucleus. But once they are filled, right, the repulsion of the electrons on the 4s and 3d will cause the 3d to be cause the 4s, sorry, to have higher energy. So that's why they write in this way: 3d1 and 4s2. Okay. So, and then of course, titanium is 3d2 and 4s2. Vanadium is 3d3 and 4s2. Now, chromium is 3d5. Why? Because if you put Ar, okay, 3d4 and 4s1, so s2, sorry. No. Now this for d orbitals, there's an extra stability for half filled D and a completely filled D. So they prefer to have the electrons will jump from here to here and from 3d5 and 4s1. Same thing for copper. See copper here, blue color, copper. See copper, right? It's supposed to be Ar, right? 3d9 and 4s2. But because the 3d10 have extra stability, so in nature they will form like this: 3d10 and 4s1. Okay, so extra stability for half filled d orbitals and completely filled d orbitals. Okay, so you can see the progression of all these things here, right? Okay, so this is the electron configuration. Now, why is scandium not in, and why is zinc not in? See, scandium, okay, go back to here. Scandium, here, scandium, sorry. Scandium. Okay, see, scandium can only form one stable compound. Of course, scandium can form Sc, can form Sc1 plus, Sc2 plus, and Sc3 plus. But these two, once they form, they are unstable. They will go to Sc3 plus. So they are not stable. They are formed, but not stable. So this is the only stable one in nature. Only stable one. Okay? And in this case here, this stable one is what is Ar, because it has lost the 3 electrons. Because scandium originally is what? Is Ar, 3d1, and 4s2. So it's lost 3 of the electrons. So that's why here there's the 3 orbitals are 0, you see. So there's no electrons in the d orbitals. That means there's none incompletely or partially filled d orbital. So scandium is not included because of that definition. It is a d block of element, right? See, d block element what? Okay, element d block. Okay, so well, it has got 1, 2, 3. They've got three ions, what? Okay, and these 2 ions, right, have partially filled d orbitals, because this one is what? Is Ar 3d1 4s1. See now. See, incompletely filled. D. This one, 2 is what? Is Ar 3 D1 and 4s0. Also what? But they are not stable. So that's why they are not into your TM. Okay. Now same thing with zinc. Zinc, of course, is zinc element is Ar 3d10 and 4s2. Okay, now this is an element. It's an element. Okay, but when when ionized, when it comes well, it will go to the only stable compound is the N2 plus, just 2. Okay, which is this one here. So this is completely filled. It is not incompletely filled. It's a deeper element. Okay, right? So that's why zinc is not included. So the 2 things here, because they don't have a stable, they don't have, both of them don't have a stable ion, okay, that is incompletely filled, that have incompletely filled d orbitals. Okay. Okay, so that's why we don't have these 2 s transition metals, right? Now, as I said, this one you can see here. All right, now let's go to the other part here. Now, the properties of transition metals are, well, they're hard and tough. That's why titanium is used as a cameras, you know, with light and very hard. They're very expensive, so they're very dense and good electrical and conductors. But the 4 important things here, which the syllabus one is melting point, high melting point, high density, the atomic radius, and the ionization energy. Now look at the syllabus, right? See, okay. They want you to talk about the melting point. Okay, the density 1, 2, density, and well, there's well, this, when you talk about this one, these 2 will include the atomic radii. Okay, to explain this atomic radii, right? Or radius lah, right? Okay, now later I'll show you about the questions on this one. Okay, okay. Now melting point, let's come to here first. Okay, first thing is melting point. Now melting point, you compare, normally melting point you compare to S block. Okay, let me show you a question that talks about that. Melting point, page 72. They always compare with calcium. See here, the melting point and density of a typical transition element such as iron, differ from those of the typical S block, such as calcium. Describe and explain. So 2 points in describe, for these two things, describe for the melting point, describe for the density, right? And explain for these two, the differences. Remember, calcium is always used. Now let's look at why, because in the syllabus they say, okay, right? Contrasts, okay, with those of calcium. So that's why they actually talk about that. Now, why? Okay, now let's look at the reason why, okay, melting point is high. Okay, yeah, right. Now, as I said here, I said for calcium, melting point is about 1,000 now, okay? But here, all is over 1,500 now, see now, 1673, 1950, all is very high, okay, except for zinc here, okay? Okay, so they're all very high, okay, high melting point you can see here, right? Now, melting point is controlled or explained by two things here, okay? Melting point, if you look at your AS, controlled by one or explained by what? Strong bonding, strong bonding. Okay. Secondly, explained by what? Structure. Right? Obviously, structure, there are two types of structure, right? Simple molecular or simple molecules, and giant structure. So metals are all giant. So they are giant structure, but here of course calcium is in group 2. They are also metals, so all metals, right? So we don't talk about structure because they are the same. But bonding, right? They are both metallic bond zone. But see, for all this from scandium right through, okay, even to zinc, right? The electrons that comes out to the sea of electrons can both come from the 4s and the 3d. Okay, the 4s and 3d, there are a lot of electrons that can come out because why? The difference in energy level is very small. So 4s and 3d can come out to be localized. That's why there's this one, a high melting point. Okay. Secondly, also because of the size, the atomic radius. Now you can see here. Now talk about the atomic radius. Okay. See here. I don't have here. Let me go to here. Okay. Here. Right. Now look at the radius. Right. This is the atomic radius. You look up here. Right. Atomic radius. Where is it? Let me show you. Top. See? Radii, atomic radii. Okay. So you look at the radius here. This is your data booklet. Right? So from scandium right until zinc. Okay? Right? They are about the same, they call it invariant. Remember why? Remember for atomic radius is the nucleus here, right? To the outermost shell. The outermost shell is a 4s. And the one before that is a 3D. See? The 3D. So as you go across the first series of your TM, right? Remember, you fill the 4s shell first, like for calcium, 4s2. The 3D is 0, isn't it? So when you go on to scandium, you are not filling in outermost shell, they are filling here. Scandium will be here, 3D1. See, 3D1, scandium. They are filling in the shell. Now you increase, so as you go across here, you are filling the inner shell. This is 3D2 and 3D3 and 3D5, right? But as you go across the period of this TM, you are also increasing the nuclear charge, number of protons. Okay, so the number of protons will attract the 4s closer, isn't it? Right? So they should decrease. But because we are filling in the 3D electrons in the inner shell, this causes the shielding effect. Okay, shielding effect. Therefore, they cancel off some of the pull of the nucleus towards the 4s. That's why, they just will decrease a bit or they will decrease a bit and increase a bit, decrease. So there's a general point of invariance or don't change much. Okay, the answer is don't change much, or they will decrease a little bit, or they're invariant. Okay, the radius is invariant. Now let me show you the question, and of course you can see the marking schema. Okay, 72. 72. All right, see, melting point and here for density as well. Okay, melting point and density for typical transition element for iron differ from those of S block. Describe and explain. Okay, now the answer, let me see this one here is what? Here this is 02. Okay, here we are. Right. So the first mark is given for both the melting point. See, the first mark is given for both black in color. Melting point and then say for iron was higher than calcium or not. Okay, now density, why? Now density is what? Density is equals to, must I explain here, mass over volume. Across the TM, maybe I explain first so that it's easier for me. Okay, now across the period, the TM period, let's go back to here. Okay, say density across the period here, right? From calcium right into here. Okay, we increase in atomic mass, right? The mass will increase, right? But because of the radius stay about the same, or because it's decreasing, so the volume actually well, stay about the same or decrease a bit. So mass increase, volume stay the same about or decrease a bit, that means the density will increase. That's why I see the density increases quite high, you know. Right? Calcium is 1.54, scandium is 3, and so forth, until the copper is 8.92. So the reason why for density to increase is, right? Now they say here, okay, they are packed more. The radius, right, decreases, and atomic mass increases. One, okay, and the atomic radius stay about the same or decreases a bit. Now also true, calcium has the atom is larger. Okay, TM the atoms are smaller size. You can see that. Okay, so they're closely packed. Right, so S block have got larger atoms. Okay, now let's look at the marking scheme here. See, iron, first of all, iron and calcium have got higher melting points and density. Okay, 1 mark for that. Secondly, melting point. Okay, stronger lattice of bonding. What kind of bonding? Metallic bonding. Why? Why more delocalized electrons? Because the 4s and the 3d electrons can be both delocalized to what? To the sea of electrons. Right? So more electrons come out. So the bonding is stronger. Right? So higher melting point. Remember I told you bonding and structure both explain melting point. Anyway, because calcium and iron both are metals, so the structure is same. They're giant structures, but the number of electrons for iron that can come out is from 4s and 3d, whereas calcium only from 4s. Why? Because 4s and 3d have a very small difference of energy level. Okay, now 1 mark is going for the melting point. So 1 mark, 2 mark. The 3rd mark is for density. Heavier, atoms larger. Okay, roughly say here, right? Larger AR. When you go across the period, right, you increase in AR, okay, because calcium is 40 and then 41 and so forth, right? But smaller, see, but same or smaller radius, so closely packed. So the idea of the radius is important, okay? So 2 things, you must have the size, the mass, and the size to explain the density, right? Because density is mass and volume, is it? So for across the period, this fella here, this is large. AR is larger, and of course the radius is about the same or smaller. Radius is smaller, so therefore density will increase. Okay, so this explains the 2 points here, right? Remember, the melting point and the density, and also the radius. So one shot, you explain three things. Now, next we go into is ionization energy, okay? Right? Now, you can see that well, one of the things about the size is they're about the same. That's why a lot of transition metals are used as alloys, see that here. That's alloys, okay? Application to make alloys, right? Because like if you got the same size, you can raise other shirts, or trousers or whatever, okay? So here we are. Now, IE, remember, ionization energy is like, for example, for titanium, okay, gas. The first IE is when they lose the first electrons, right? The energy required to lose the electrons from a gaseous atom. Ti, positive, gas, plus E. And this is the first IE. Okay, so here for titanium, remember, right, is of course AR. Okay, remember titanium, let's get this. Okay, here, okay, titanium, right? The me is 3D2, 4S2. Right, now it's coming from the 4S because 4S now has repulsion from the 3D, the high energy level. So this is a 4S electron. So here is your AR, 3D2 and 4S1. Yeah, that means all of them, every one of them, you can see every one of these fellows here, but the first IE comes from the 4S1. All of them. Okay, right? Now the second IE for titanium also comes from 4S. All the 4, this is from 4S1, this is from 4S2, the second electron, except for chromium, because chromium is what? Chromium is AR, 3D5, 4S1, because of the special extra stability of the half-filled orbitals. That means that if this is chromium, right? So for first IE, chromium will go to Cr, positive gas, plus 1 electron. Right? Now this, of course, is this one here, and this is your AR, what? 3D5. Okay. So for chromium to go to Cr2 plus, which is your second IE, gas plus 1 electron, this one will come from what? Come from the 3D, right? The 3D5, because this will be AR 3D4. That's why it needs higher energy because of the extra stability of the 3D5. Similarly for copper, because it comes from the 3D10. Okay, right? So mainly what first and second IE comes from the 4S1 and 2. That's why you can see here progressively. It's a nice graph. Okay, right? Okay, now the first one is about the same one because IE, ionization energy, right? The size of it, the value depends on two things. One, of course, the nuclear charge, the amount of positive charge protons there, nuclear charge. Secondly, the radius or atomic radius or ionic radius depends, okay? For I2, the ionic radius, okay? Okay, now of course this one here, right? I already explained to you the radius about the same or decreases because of the shielding effect of the filling of electrons in the 3D inner shell. Okay, so you can see that this one is about the same, right? So because of the infilling electrons, then will reduce the pull. Filling of the 3D inner shell reduce the pull of the nucleus towards the outermost electrons. That's right. It's about the same. But you can see here from the third IE here, see, of course it's higher, right? Because to take the third electron away, the stronger pull of the nucleus towards the 3D. So all these are 3Ds. Okay, all this will be from 3D electron. Now, you see there's a kink up here and down here. This one is from manganese. Okay, manganese here. Why is it extra high? Now manganese, remember now this is a third IE here. Third IE. Okay, it's going from Mn2 plus to Mn3 plus. I'm withdrawing the third electron, so it's Mn3 plus. See? Okay, here, Mn3 plus. Huh? So remember, now Mn2 plus is 3d5, you know. Okay, because Mn, remember Mn is Ar, 3d5 and 4s2. So to lose two electrons is coming from here, right? 2 electrons coming from here. So from here to here, it will be lost two electrons from 4s2 and it's 3d5 here. So to go to 3d, to go to Mn3 plus here, it must come from the 3d5. Of course, this one have what? Extra stability because of half-filled d orbital. That's why it's a bit kinking up here. Okay. Now iron is going down here a bit. It means it's not according to like this. This will be the general trend. Okay, this is the general trend. So it's a bit up here, higher energy. It's a bit lower. Why? Because of the stability against of the 3d5 for Fe3 plus. So Fe2 plus gas going to Fe3 plus. Fe2 plus, right, is 3d6. Okay, because iron, let's put it out. Iron is what is Ar, 3d6 and 4s2. You know, this is iron. So iron 2 plus, of course, is gone up this one. So 3d6 going to this one, the extra stability. It means easier to go forward. That's why they require less energy. Okay, so whenever you can see a disturbance in IE up and down or kinking up, kinking down here because of the 3d5 or 3d10. Okay, okay. Now this is finished. Now you can see here. Next one, of course, is variable. We got to go to chemical properties. Now, basically, I included these two here as chemical properties, but normally this 4 here or 3 here is the main chemical properties, and they also ask. Let me just stop a bit for a while, okay? Never mind. Let me see. Okay, pause a bit. Okay, I just thought of showing you this question. Now, they ask you for, we have finished most of the physical properties, okay, which is definition of transition metals, the radius, the density, the melting point, and also some of the electron configuration. Okay, now here they ask you, describe 3 characteristics of chemical properties. See, they ask you for here, chemical properties. Describe, means tell you what they are. Of transition metals that do not show by group 2 of calcium. 3 of them, 3 marks. Okay, now let's show you the marking scheme. Okay, the 3, all right, colored compounds. Okay, color. Color is one of the last thing we will do. Okay, colored compounds, colored ions. Okay, variable oxygen state. We're going to do this now. Okay, variable oxygen states. And of course, there's formation of complex, which is the next one, and catalytic activity, right? So the 4 of them can choose, so give 3. Okay, now look at this here. Okay, we go back to page 16. Okay, right, now here I gave you here, right, see, variable oxygen states, complex formation, color, and catalyst. Right, so I put this in here because you need to calculate a few of this complex formation thing. Okay, so now variable oxygen state. Variable means plenty, a variety, and they happen quite a lot. No, see, right? See here. Now these are all the variable oxygen states for the first row of your TM. Scandium, you can see the only one. Of course, it's +2, +1, but they're not stable, see? Same as zinc, okay? Only 1. That's why these 2 first are not included in your transition elements. Now, for titanium, right onto copper, you can see titanium has got 4. Ti1 plus, Ti2 plus, 3 and 4. Now, the circled ones here are the very common ones. 1 and 2, they exist, but they're not very common. Vanadium, there's 1, 2, 3, 4, 5. Now, see, vanadium come out in exams, no? Vanadium, remember that? How do you know this one here? You know, if you look at your data booklet, okay, this one here, right? Look at your E0 values. You've done E0 values before, isn't it? Right? You can see here, the E0 values here, and see all the 4 oxidation states. They actually ask you later. Oh, sorry, I passed it earlier. Here. Here. Okay. See, vanadium. I just rub it off first. This is the vanadium. See, vanadium. Right. And of course, E0 values are used later in your TM to ask you to calculate things. Okay. Now, see, 1 plus is not very common. Okay. 2 plus, 3 plus, is 4 plus. Okay. It's 4 plus, right? They ask you now VO2 plus. Okay. You look at it, the whole thing here. This minus 2, right? So you put, let's say it's X here. So it's 1 times X plus 1 times minus 2 is plus 2. So X is what? It's minus 2 go to plus 2. X is equals to plus 4. Remember, oxidation always put the plus first. Okay, now. Okay, plus 4. And of course, this is plus 5. See now, these two are same. These two are same. Right, plus 5, you work it out, VO2 whole thing is 1 positive. Why not? Okay. So here, of course, is this minus 2. So it's, let's say it's X here. So 1 times X plus 2 times minus 2 gives you plus 1. Right? So X minus 4 give you plus 1. So X equals to plus 5. Same with this one here. Right? This one here. This one, of course, VO3 1 minus. I work it out here. So this X here. So 1 times X plus this minus 2 for oxygen plus 3 times minus 2 give you minus 1. So it's X, right? Plus minus 6 gives you minus 1. So X equals to plus 5. So these two complex ion here, you can see later, are actually plus 5. So vanadium got 1, 2, 3, 4, 5. But of course, 2, 3, 4, and 5 are quite common. That's why I can see here, right? Vanadium 2, 3, 4. So it's variable oxygen states. Why? Because they come from the 4s2 and 3D what? 4s or 4s and 3D lah. Why? Because the 4s and 3D, right, can be ionized, can be lost easily because there's a very small difference in energy level between them. Chromium is in more. Plus 2, plus 3, plus 4, plus 5. Plus 1 normally is not, it's not very stable. They form like they're formed, but they're not bothered about plus 1. Chromium plus 6, of course, you can see what in your CR, dichromate, CR, remember this one here, 2 minus. And also for your chromate, 4, 2 minus, you work through, I won't go through, okay? And then manganese got 2 to plus 7. Mn 2 plus, of course, famous. Why? Because in your titration, because this is your faint pink, okay? Right? Of course, it's plus 7 is your MnO4 minus 1. Remember? Right? Manganese 7, or we call it permanganate. This is the purple color solution. Okay? So you can see the variable iron got so many, okay? As you go down, you less and less. Why? Because the nuclear charge increases, the pull of the nucleus towards the outer electrons becomes stronger. So as you lose electrons, they become harder to lose. Okay, that's why it decreases here. But the interesting thing is, they all have plus 2 and plus 3. Very important, these two here. These are the common ones. Okay, plus 2 and plus 3. Okay, until here. So, right, plus 2 and plus 3 are common right throughout. Now they found that plus 3 is more stable or more common, right, at the beginning. But at the end, you see, see, circle, 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 round. Okay, circle, circle. Okay, because Mn2s, forget about it. Okay, these are more common, more stable. Okay, so of course 2 is stable, but as you go here, 2 become the more stable ones. Now you can see these in the electrode potential. Now before that, see, now questions are asked like this. They ask you to even predict, what are the oxygen, why, first of all, why are they variable oxygen states? Okay, let's go to page 72. 72 question. Okay, right. suggests a reason why iron forms compounds containing Fe3 plus as well as Fe2 plus, and why calcium only contains 2 plus. Okay, now this one question here, and the other question of course is 103, about the same 103, which I think is better to use to explain. Okay, suggest why transition elements show variable, see now here they say variable oxygen states in the compounds, whereas S block calcium do not. Okay, now here's about 2 marks I think, right? Now let's see why. Okay, let's see what year is this. Okay, 13. I think it's here. Right, see, for your transition elements, right, electrons from the 4s, the color first, blue, see, right, electrons, many electrons of similar energy, about the same, from what, 4s and 3d in a valence shell orbital, can be lost, can be used, is available for bonding. 4s and 3d, many, because you have 4s2 and 3d1, 4s2 and 3d2, 4s2 and 3d3, 4s1 and 3d5, now all of them can be used. Why? Because the 4s and 3d orbital shell energies have similar, right, or very small difference, or say small difference in energy level. Therefore, they can be lost easily, you see, right now. So as they lose, it becomes positive charge. For example, right, Fe to go to Fe2 plus say 2 electrons here, and Fe to go to Fe3 plus 3 electrons here. Right now. The difference in energy level between this one, the one electron here is very small, so they can be lost easily. Right? Okay, or I can say successive energy rise steadily. Okay, this one and this one are the best explanation. Okay, why there's very similar energy levels. Okay, why there are so many oxygens, variable oxygen states. All right, now this is not fair. Now, let's go back to the one that's page is 17. Okay, right. Now I describe my notes here. Describe the tendency for transition elements to have variable oxygen states. Many electrons in the 4s and 3d, right, because combined can be used for bonding, can be lost. Okay, small difference in energy between the 3d and 4s orbitals. So they form, but they can be, they can lose easily 4s and 3d. Okay, now this is the thing to explain this too. Okay, the plus 2 and plus 3, now they actually comes out to ask you to predict, page 73, to predict compounds formed by this. For example here, see now, okay? Of course, this first is very simple. See, titanium is important, blah, 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 and high, blah, blah, blah. Write the electron configuration for titanium. This is easy, isn't it? Okay, now we go to it. Titanium form 2 chlorides. It's just possible formula. See, if you know that plus 2 and plus 3 are very common, right? So you can put TiCl2, TiCl3. See now? So they ask you, these kind of things they ask you. Okay? So you use your ideas to see that, the triangle. Okay, page 17, the triangle here. Okay? Here, right? To see, well, as it goes up to manganese here, they've got the plus 2 and plus 3 are very common. Now let's explain how use the electric potential to explain the plus 2 and plus 3 idea here, which is common here. Okay, so it's called the relative stabilities of aqueous ions. Okay, now here, a lot of junk here. Okay, but never mind. Maybe I just write a bit here. Have to explain easier. Okay, now I should have done this. Sorry about this. Right now, remember these are electric potentials. Remember, they are reduction potentials. Remember, you always use reduction potentials to explain in your exams. CIE, the marking scheme, always use reduction potential. What do you mean by that? Reduction potential means what? Means the E naught given in your data booklet. Okay, now let's let me go through again. All right, just in case you don't know this. Now these are all what? These are all reduction potentials, right? See? Right, all these are given here is reduction potential. See, plus electrons, but this is reduction potential, not oxidation. So you use this one to explain. Whether minus positive, you use the original to explain. So your explanation must be geared in a way to explain what the relation is about. Now here, right? See again, reduction. Because Mn2 plus M, of course here means that M, M, for let's say titanium is M is titanium, right? 2 plus aqueous plus 2 electrons, well, reversible to give you titanium solid. Okay, and here of course the E not the E potential here is your for reduction here is minus 1.63. Okay, so of course this reduction thing is not very good to explain about the reactivity of metals because it's the metal. Okay, so normally if you become an electrical mechanical engineer or whatever, you want to talk about the alloys, the metals, right? This is the metals. How reactive are the metals? Like titanium metal is used in medicine to form this ball. What this is? This socket, this ball and joint socket in your hip bone or your shoulder bone. If you break it up, they use titanium to replace it. No, why? Because they say, well, titanium is very, very stable, very unreactive, very light, very strong. So these are properties that they use to replace a hip socket bone. Okay, but is titanium reactive or not? Now you look at it here, it's pretty reactive, minus, right? This go backwards, means from titanium to here is positive 1.63. All this show you, all this will show you here to here that the TM from titanium to nickel, the metals are quite reactive comparatively to hydrogen. Now, let's see here. I got down here. Okay, see the two things of metals, right? Metals, remember here, metals, they react with two things here I talk about is with acids. And of course, daily life, there's not much of acids, see? But daily life, there is Batman and Robin duel. Water and oxygen, these two are main oxidizing agents, right? In nature, oxidizing agents. So, let's go to the first one first, okay? Now, all these metals react with acid. Right now, here, this is easier for you. Titanium, right? Now, remember to go from titanium solid to here is positive, okay? Right? And if you put titanium into acid, they will react. See now, here's 0.00, right? So titanium with HCl is a E cell is plus 1.63. That means they will react. They're very reactive. Similarly for everything except copper. See, copper will not. Because copper is what? Copper is positive 0.34. That means it will not react with water. It will not react with acid, right? Because you go from copper backwards, right? It will be positive, isn't it? Right? Now the current is off, but we are okay. Right? So here the copper. Just excuse me for a while because there's a lightning. I need to pause it for a while.